So this is recursion. I'm going to talk you through the programming technique called recursion. It's a very powerful technique, and I'm going to use these two examples to talk through it. They are factorial and Fibonacci. So let's start with factorial. So factorial is a mathematical operation, and it is timesing a number by the number before that, and so on until we go down to 1. So 10 factorial is as described below there. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 4 factorial would be 4 times 3 times 2 times 1, and so on. Now you very quickly get to a very big number in the sequence, and processing that would take time in the computer, and writing the code just to add on these next numbers after each other takes a little while. But we can do it in a different way. We can do it in a recursive expression. So if you have a look at this, so we're talking about n in terms of itself. So n factorial is here. So n is the number that you want to plug into it. So you plug in 5 factorial there. So put in a 5. And then it equals 5 times then n minus 1, which will give you 4 factorial. So you're putting that back into this expression, which in itself would be 4 times n minus 1, which is 3 factorial, which we put back into the expression, and so on. And you keep going back through the expression. So just see how that plays out. I'm going to put in the number 10. So there we go. So that's what it will look like. So 10 factorial is 10 times 10 minus 1. And then we look at the bit at the end, and that's actually the same expression. So we go back into another version of that expression, put in the 9, and the 9 is the 9 minus 1, which is 8. So we need to put the 8 back in. So then we're in another expression, and 8 factorial is, and so on. You can see 8 minus 1 would be 7. So let's keep going. And where does that take us? So if we keep going, we get down to 1. 1 factorial equals 1 times 1 minus 1 factorial. 1 minus 1 is 0. 0 factorial. So 1 times 0 factorial. What's 0 factorial? That would be 0 times itself, which is 0. So it all seems to be going wrong now. And 0 would be 0 times 0 is minus 1. So something's happened here. It's working well. Something's gone wrong. And what this is telling us, we need to have some kind of stopping state or end state. And our end state is 1 factorial. So go all the way down until you get to 1, and then stop, and then go back, and this is what we say, unwind, and then give us the answer. So let's have a look at that as a function in Python next. So I've called it factorial, and I've just written 5 in here, just going to give it 5 there. And we have an end state. Our end state is if n equals 1, return 1. So that was our end state. Otherwise, coming down here, you have return n times factorial of n minus 1, which is what we saw in that expression before. So that was the bit that we kept recursing with. So that calls another instance of that function from within the function. It keeps going until it gets to the end state, and then by returning it unravels, and then in the end it will give us our answer, and it returns it. And at the bottom there you can see we're printing what it returns back. Okay, let's have a look at this and see what it looks like in another visual way, help you understand. So the box represents the function, and we're putting 5 into that, and 5 is put in, and then n times n minus 1 factorial is the expression. Let's stick that at the top there, and we'll look at the end part, the 5 minus 1, that becomes 4. So we call another version of the function. It's within that first function there. Look at that, it's called from within, and now it's calling the 4. 4 minus 1 is 3, so that needs to call the 3 function. So we're doing another function, 3 times 3 minus 1. 3 minus 1 is 2, so we call that function. And then once we get to there, 2 minus 1 is 1. 1 factorial is our end state, and if we hit that end state, we start to return. So let's go backwards now. It's our end state, start to unwind. We'll go backwards, and 2 times 1, put it back in here. 3 times 2 is 6. That goes back to here. 4 times 6 is 24. That goes back into here. That's where we called it from. That's the value. That's what it's returning. And then 5 times 24 is our answer. So we have 120. Okay, clever stuff. Right, now, Fibonacci. Fibonacci is next. If you don't know this sequence, Fibonacci is a mathematician. And the sequence is you adding up the two numbers previous to get the next number in the sequence. So if you look down, 5 plus 8 is 13, 8 plus 13 is 21, and so on. So there's two things there we're looking at, which means that if there's two things there, we're going to need to have two different callings of the function. So it looks a bit different in Python, and this is why it's a nice one to look at as well. So here's the function. I've called it fib. I've put in fib5, and we have, if you look here, we've got two end states, if n equals 0 and if n equals 1. And if you look at the expression below, we're adding together the n minus 1th term, which is the one before, and then the n minus 2, which is 2 before the number that you want. So you give it a number that you want. So the fifth, in this example, the fifth term in the sequence. And then we look at the fourth term in the sequence and we add it to the third term in the sequence. And the sum together gives us the value in Fibonacci. So if we look through here, so here's a sequence. So if you type in 5, it should give us 5. If we type in 4, it should give us 3. If we type in 3, it should give us 2. And if we typed in 6, it would give us 8, because 3 plus 5 is 8. So this one will recurse down until it gets to the end states of n minus 1 and n minus 2. So that's why it's two different end states, because it's going to be subtracting 1 or 2 from the value n. So if it gets to 0 here, it's going to give us a 0. So we add nothing on. If it gets to a 1, it returns a 1. So we add a 1 on, and so on. But we'll just see how that plays out. So visually, we're going to draw it like this. So it looks like a tree, and it grows like a tree. So we put in 5. And then n minus 1 is 4, but n minus 2 is 3. So now we've got two versions of Fibonacci that we've called. Now this one here, this instance of the Fibonacci function, is going to call n minus 1 and n minus 2 itself. So we call a 3 and we call a 2. And this one's going to call an n minus 1, which will be a 3, and an n minus 2, which will be a 1. And then going along, and it grows really quickly now. So it's every time we seem to be doubling what we've got. So the 3 would call a 2 and a 1. A 2 would call a 1 and a 0. The 2 here would call a 1 and a 0. And a 1 calls, well, a 1's an end state, so it calls nothing. All the way down here, we can see that 2 is called a 1 and a 0. Now, these are all end states, 1, 0, 1, 1, 0, 1, 0, 1. So there are end states. Now, at this point, we can actually see that we're going to start to unwind. So we've hit all our end states across the board. So let's go back then. I've just grayed it out, and then we'll see what happens and what gets returned. So quick look back at the function here. So if n equals 0, return a 0. If n equals 1, return a 1. And then add the result together. So the 1 returns a 1. The 0 returns a 0. We add the result together. 1 plus 0 is 1, and that goes into 3. Now this returns a 1, so the 1 plus 1 will be 2, and the 2 is what gets returned to the 4. Now the 4's here, we need to complete this side. So the 1 returns a 1, the 0 returns a 0. We add those two together, and it will return a 1 plus a 0 to the 4. So now the 4's got a 1 plus a 1 and a 1 plus a 0 coming in. So 1 and a 1. A 2 and a 1. A 2 plus 1 is 3, and that goes up into the 5 here. So that's the result of that gets returned to the 5, the original calling version of the function. And then this side of the tree, we have a 1 and a 0 being returned, a 1 plus a 0, a 1 here, and a 1 plus a 1, which will be a 2 coming up here. So adding that together, so 3 plus 2 is 5, and the result is, for the 5th term, is a 5. I didn't do it for the 6th term. It would take up too much of the screen space there, but it will grow and grow and grow as a tree. So you can imagine the size of these things with the bigger numbers. But that's how many instances of the function that it would have generated to do that. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We've got 15 instances of the function which have been created just for the number 5. So there we go. That's number 5. This is the 5th one in the sequence. And you can code that in Python. You can see that work yourself. So you can put that into Python, put in some different numbers. You can put in some print statements, and then you'll actually see what's happening on each stage, and you'll see how many versions of the function that it records. Just putting a print statement in every time it's called, and printing the value of n will give you that. Okay, I hope you've understood that.